Okay, y'all, so this is the last video in this unit, and this is the geometric probability distribution. So in the last video, we did the binary probability of distribution, and then this is the geometric. And so you're going to see this looks super similar to what we did in the first one. So we still use this acronym of BINS. And B is still binary, so you have to have two choices. You have to show independence, and you have to be able to show probability. So these things are all the same. What's different now is when we get to the number part. So in the binomial distribution, what we said in the binomial distribution is n was our fixed number of trials. And that's what we had in the binomial distribution. Now, what's different in the geometric distribution is now this number of, the number part of it is the number of trials is unknown. So our number of trials is unknown. This is what it makes it different. So what we're looking for this time, our n value here is going to be the first success. So prior we would say we had 40 different trials, and now we don't know this, so our n value is to our first success. So we do not have a set or a fixed number of trials. All right, so a geometric setting arises when we perform independent trials of the same random process and record the number of trials it takes to get one success. On each trial, the probability must be the same, so that hasn't changed, okay? So here, X is unknown, but we're searching for the first success, and this is different than the binomial, where X is a fixed number. So some examples of the difference between the two, binomial and geometric. How many times do you have to flip a coin before you get tails? How many times do you have to roll 2 dice before you get a sum of 12? How many throws at the dartboard until you hit the bullseye? How many people will walk through the door until a man walks in? So these are all things where n is unknown. All right, so let's look at this. So this says, if you roll a 6-sided die, so we're going to roll a 6-sided die, let's see how we get these different scenarios down here, okay? So X is the number of trials until you roll a 6. So this is what makes it different in a geometric. All right, so let's look at this. What is the probability that you roll a 6 on the first trial? Well, our probability statement doesn't change. So the probability that we get it on the first trial, that all remains the same. So if we're going to roll a 6-sided dice and we want to roll a 6, our probability is still 1/6. This says, what's the probability that you roll another number the first trial, but you roll a 6 the second trial? So what this is really saying is, what is the probability that we roll a 6 on the second trial? So if we look at the math of that, that means the first trial, we have a 5 out of 6 chance. And this right here, this is actually for a failure. And then the second trial that we want is our success. So it's 1/6. So the probability that we would get it on the second trial would be 5/6. What is the probability that you roll the number, roll another number on the first 2 trials, but a 6 on the third? So we're saying, what is this? And now we know we have a failure, and then we have a failure, and then we have a success. Okay, and then on this last one, we're going to roll another number the first 3, but a 6 on the fourth. So failure on the first one, failure on the second one, failure on the third one, and then we get a success. And so hopefully you see we have this pattern here, but what happens is if we don't, this could be a lot of different math. So what happens is we're going to set up our formula. So let me just fill out this table real quick. So using the 4 outcomes above, we're going to create this table. So what we knew is that on the first one, it was 1/6. And on the second one, it's 5/6 times 1/6. And then I have 5/6 times 5/6 times 1/6. And on this last one, and hopefully you're seeing a pattern right here. And that pattern is going to play into when we get to our formula here in a second. But let's ask ourselves a couple of questions. Can x be 0? And the quick answer to this is no. So because this is geometric, x is the number to a success. So that number might be 1, but the number cannot be 0. Now, let me make a little note here. X can equal 0 on a binomial distribution. So there's a difference. So x can equal 0 on a binomial distribution. It cannot be 0 on a geometric distribution. Okay? So the next question here says, when do we stop the table? So can I keep doing this until I roll a 6 on the 5th try, or the 6th try, or the 7th try, or technically, so in theory, we never stop the table, which means we can have infinite number of tries. And it also means, in theory, we could go on forever without a success. And we know that's probably not going to be true, but in theory, we could go on infinitely. So what is the pattern that we're noticing? So I'm going to put this in words, and then we're going to go straight to the formula. So what we notice is the probability of a failure, and this is going to be n. So we have the number of failures. I don't want to use letters yet. So the number of fails times the probability of a success, and that exponent is always going to be 1. So what does this look like in math terms? So we have p is the probability of a success, and x is the number of successes. We have no n value. Remember, we have an n value in our binomial distribution. So probability that our random variable equals some number of successes, my formula becomes 1 minus p, and then I have x minus 1 times p. So if we look at our formula up here, what I really have is this becomes 5/6 to the 3rd times 1/6. Well, if I know it takes me 4 times, if I write this, I would have the probability that x equals 4 would be 1 minus 1/6 to the 3rd power times 1/6. And so this formula would simplify to 5/6 cubed times 1/6. Now, this part of my formula right here is the fail, and this part is the success. So what does this look like in terms of mean and standard deviation? Well, our formulas are a little bit different this time. So now our mean with regards to our random variable is going to be 1 over the probability. And this probability is the probability of success, right? Probability of success. And our standard deviation for our random variable is going to be the square root of 1 minus the probability of success all over the probability of success. And you'll notice that only the numerator is under the under the square root bar. Okay. All right. So let's do some examples here so that we can kind of see how this works. So what we have is this first one says, explain how each of the following fits into this geometric probability. So you toss a coin until you get a tail. So this is what I'm looking for. So my x variable is the number of trials to a tail. Tail is my success. So for my binary, I either am going to have a head or I'm going to have a tail. So is this independent? Yes, it's independent because it doesn't really matter how many times I flip a head because what I'm looking for is a tail. So my number here, this is going to be the number of flips to a tail. And my probability, my success, which is my probability for a tail, is going to be 0.5. All right, so what this says is x equals 4. So my probability that x equals 4 is going to be 1 minus 0.5. So this is my success probability. And I'm going to have the 4 minus 1, because it's the total number minus the 1 times 0.5. And if you see this, if I simplify this out, I get 0.5 cubed times 0.5. And because these numbers are the same, it's like saying 0.5 to the fourth power. And so the probability that I would get a tail on the fourth try is, hold on, let me find my calculator here. 0.5 to the fourth power, which is 0.0625. Now, I'm going to do a little justify here just so we know what we found. So the probability of the first tails on the fourth flip is 0.0625. All right, let's try another one. A company reports that 75% of the emails it receives are spam. So what do I know? X is going to be the number of emails until we get spam. Oh, S-P-A-M. Okay. So my binary criteria here is either spam or no spam. Are they independent? Yes, they're independent. And I'm not going to go into the detail why. They're independent because it's either spam or no spam. Okay. N here is going to be the number of emails until spam. And the probability of success. So my probability of success here is going to be 0.75. And this says, find and interpret x equals 2. So I have the probability of x equals 2, and that's going to be 1 minus 0.75 to the 1 power. So it's 2 emails minus 1, so that's my formula, times 0.75. And this is an easy one to just kind of see. You have 0.25 times 0.75. That's how this simplifies. So the probability of x equals 2 is going to be, let's look at this, 0.1875. Now, my justify, just so we know what we found here, is probability the second email opened is spam is 0.1875. All right, so type A blood is found in 43% of the population. So I think you're getting this part over here. So what we have is the probability that the fifth person that we test has type A blood is going to be our formula here of 1 minus 0.43. We had 4 failures before our positive one, which is 0.43. And if I plug this in, right, and then one last justification here. So the probability the fifth person tested is the first with type A Probability the fifth person tested is the first person with type A blood is 0.045. Okay, so we did all this by hand. We know that we've got these tricks in the calculator, so here's the difference. So we have, just like with binomial, we have cumulative and PDF. So PDF and CDF, probability distribution function, this is my PDF. Again, this is when we know the probability. So all of these we could have solved with our geometric PDF. And what you'll notice, this is a screenshot here of the calculator. So binomial PDF and CDF, and then down here, this is the geometric PDF and CDF. So they're both right here on the same screen. And this happens when we have an equality. Then our CDF, which is our cumulative distribution, this happens for the interval. So this is, again, when x is less than or equal to x, and it has to be less than or equal. So just like with a binomial distribution, you may have to change if it's only less than or if it is a greater than or equal scenario. So we have to have this as less than or equal. Okay, so let's practice this for a second. Hold on, I know I have another piece of paper here. I thought I did. Oh, it's on the back. Sorry about that. So here we go. We're just going to use a calculator and we're going to knock these out real quick. And so this first one says, type A blood is found in 43% of the population. What is the probability you will not find a person with type A blood until the third student walks in? So what is the probability that the third student is going to be type A blood? So I've got everything else that I need up here. So I have 1 minus 0.43. I'm going to have 2 failures before the third person walks in. And that's what this is saying. So I'm going to use, because this is an equality, I'm going to use the geometric PDF. Now, let me repeat this. This is required on the AP test. You've got to show that you understand the formula. Then we're just going to plug it into our calculator. So if I go in here under distribution, and I'm going to go to geometric PDF, my p-value is my probability of success, which is 0.43. My x value here is third, my third person tested. And what I get is that the value of this, so p of x equals 3, is going to be 0.1397. And I'm just going to go to 4 decimal places because that's kind of a funky one to round. Okay, now I'm going to do this just to kind of show you the difference. If I go back in here and do a distribution and I go to binomial PDF, you know, it's asking me for the number of trials. So if I say, well, it's 3 trials and my success ratio is 0.43, oh, sorry, that's not what I want. So let's just say I have a whole bunch of trials. What's the value that this is 3? I get this domain error because I can't have this unlimited amount of trials. That's why we have to use this geometric PDF. Because remember, we don't know how many people it's going to take. We're going to say, okay, what happens when it's the third person? What is the probability of that? So that's why we get this domain error when we try to have just this unlimited amount of trials. All right, so type A is found in 43% of the population. What is the probability that you find the first person with type A blood is within 5 students? So what this is saying is the probability that this is within 5 students. So that means 5 students or less. So if you remember with binomial, we said the probability within 5 students, so it's 5 students or fewer. Well, this is a classic CDF. I don't have to make any changes to this. So what I have here is the probability x is less than 5 is the probability that x equals 1 plus the probability that x equals 2 plus yada, 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 the probability that x equals 5. So that would just take a whole long time to plug it in. This is what it would look like, though, if you want to justify this on a free response. And now I'm going to go in here and do distribution, geometric CDF, which is the last one here. Oh my gosh, I'm so sorry. So my probability of success is 0.43. My x value this time is going to be 5. And what we get is that this probability is 0.9398. All right, so last one. And all the words here say is that, you know, we have to adjust our binomial, or we have to adjust our formula with a complement if we have a greater than or equals, just like we did with the binomial. So what this says is a type A blood is found in 43% of the population. What's the probability it will take more than 3 people? So what does this look like? It's going to take more than 3 people. Now it doesn't say 3 people or more, it just says more than 3 people. So if I look at this, 2 people, 3 people, 4 people. So if it takes more than 3 people, that means this is what I'm looking for. Because remember, it's discrete. So what we're looking for is more than 3 people. So I'm going to rewrite this, and I'm going to say this is going to be, because we want everything that's this direction, 1 minus the probability that x is less than or equal to 3. So if I want greater, so I'm going to use the complement. I'm going to include the 3 on this because it just says more than 3 people, so it's starting at 4. All right? So what does this look like? 1 minus 0.43. This is going to be 3. Oh my gosh, I'm having a brain fart at the moment. Yes, this is going to be 3. And then this is going to be 0.43. Now, why did I use 3 here? I used 3 here because this value of 3 is what I want. So it's the 4th person that's my positive number. Okay, so up to 3 is what's a failure. It's the 4th person that's positive. That's why this exponent is a 3. Okay, so I can plug this in and I can say 1 minus, I'm going to go into my distribution, and I'm going to have geometric CDF. That's the same, and this value is 3. And this tells me that this value here is going to be 0.185. Okay, last question. So I talked about this earlier in the notes today. So what happens if we want to find a mean and we want to find a standard deviation? So here are my formulas for mean and standard deviation. And all we're going to do is plug these in. It's really simple in this case. So a local fast food restaurant is running a draw 3, get it free lunch promotion. After a customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer pays the bill. So let X equal the number of customers it takes to get a first free order. So how many does it take to get the first free order? So this is what makes it geometric. And so what I know here is that the probability of a success, so the probability that our card is a 3, is going to be 4 over 52. There's 4 3s in the deck of 52 cards. All right. So if I look at what this is, what is the mean here, calculate, interpret the mean, then I have the probability of success is going to be 1 over 4 over 52. And if I do that in my calculator, this is the same as 52 divided by 4, which is 13. All right, so my interpret, what does this mean? It means the first free order when a customer draws a 3 would be around the 13th customer. So it would take 13 customers for us to roll that 3. So calculate, interpret, standard deviation. So I have my formula, and I have 1 minus p all over p. So what does this look like? It's 1 minus 4 over 52 all over 4 over 52. And I'm not going to get fancy with all that. I'm just going to plug that straight into my calculator. So the square root of 1 minus, I'm going to use a fraction just so I don't mess this up. And this whole thing is going to be divided by 4 over 52. And so the value here, so 12.49 is what I got. All right, so let's look at our interpret on this guy. So the restaurant runs a promotion. And actually what you might even want to say is the restaurant runs a promotion for many days. That would be a good thing to say. And so we would say the first free order varies from the mean of 13 by 12.49 orders. That's pretty significant. So basically we're saying from, oh, that's a 9, from 1 order to 25 orders. I mean, that could be a lot of free lunches. Think about that. Okay, that was it for geometric.